So in the previous video we have seen questions related to Riemann integration. Today let's start with discussing questions on convergence of improper and infinite integral. So it is also one of the important topics in real analysis, as a lot of questions are asked on this topic. So let's see how we should approach these type of questions. So while solving a question on convergence of improper and infinite integral, your first step should be to find out the points of infinite discontinuities that are there in the given integration. So we'll do that for this function. So if you observe that, if I just substitute x equals to 0, so at x equals to 0, my log x function approaches minus of infinity. So we have an infinite discontinuity at x equals to 0. Infinite discontinuity at x equals to 0. Also further in the video I'll write infinite discontinuity as id, because it will be inconvenient for me to write such a long term again and again. Likewise, if I check at x equals to 2, we have this. Again we have infinite discontinuity at x equals to 2 as well, because the denominator is 0 when I plug in x equals to 2. So here also we have infinite discontinuity. Now if you observe that apart from these 2 points, our function is a proper function. Apart from these 2 points, these are the only 2 points of infinite discontinuity. Therefore x equals to 0, 2 are only points of infinite discontinuity. Now let's just name our integration as I for convenience. So it is 0 to 2 log x divided by square root of 2 minus x dx. Now what I'll do is I'll just break the integration in 2 parts in order to separate the infinite discontinuities. So it will be integration from 0 to 1 log x divided by square root of 2 minus x dx plus integration 1 to 2 log x square root of 2 minus x dx. Also one more thing, I used 1 here. You can use any other number as well, but we often use 1 because most the convergence changes at 1, especially for P series. Convergence changes at x equals to 1, so it's better to take this because we'll be using P series a lot while checking, while using comparison tests. So it's better to try to break it at 1 only. So now let me name them as I1 and I2. So this integration is I1 and this one is I2. So now what I'll do is I'll just check their convergence separately. First I'll check convergence of x1 and then I'll move on to check convergence of x2. Now my I1 is integration from 0 to 1 log x divided by square root of 2 minus x dx. Now I can write it as this as well, integration from 0 to 1 minus log x divided by square root of 2 minus x dx, which will be equals to integration from 0 to 1 minus of fx dx, where my fx is equals to minus log x divided by square root of 2 minus x. I have taken this negative sign because as x approaches 0, my log x function approaches minus infinity. So to make the integrand positive, I have introduced the negative sign. So now let's see how we can use comparison test here. So if I assume any function gx as 1 by square root of x, now what I'll do is I'll use limit comparison test to see if the following integral I1 converges or not. So if I calculate this limit, that is limit x approaches 0, fx by gx, it will be equals to limit x approaches 0 minus log x divided by square root of 2 minus x divided by 1 by square root x, and this can be written as limit x approaches 0 minus log x times 1 divided by square root of 2 by x minus 1. Now if I plug in 0, it will be basically infinity by infinity form, and that's indeterminate form. So in order to calculate its limit, I need to use L'Hopital rule. So if I do so, I'll get limit x approaches 0 minus of 1 by x divided by 2 by x minus 1 raised 3 by 2 times minus 2 by x square, and that simplifies to limit x approaches 0 x by 2 2 by x minus 1 raised 3 by 2. Now if I plug in limit, it will be numerator is 0, denominator is infinity, so it is 0 upon infinity, that is 0. So the limit turned out to be 0. Now observe, when we use basically comparison test, so the condition is that this limit should turn out to be non-zero and finite, but in this case it turned out to be 0. So we have a special case when the limit is 0, that is if limit x approaches, let's say a, and here a is basically point of infinite discontinuity, fx by gx is equals to 0, then if integration, let's say x1 to x2 gx dx converges, then that implies that our integration x1 to x2 fx dx also converges. But we cannot say anything about like if fx converges, then we cannot comment, like if gx diverges, then we cannot comment about divergence or convergence of fx. Likewise, there is another special case, that is if this limit, that is x approaches a, fx by gx is equals to infinity, then if integration x1 to x2 gx dx diverges, then that implies that integration from x1 to x2 fx dx also diverges. So in our case, in our question, our limit turns out to be 0, so we need to check if our function gx is convergent or not, because then only we'll be able to comment on convergence of fx. Now if I check my integration of gx, that is integration from 0 to 1, my gx is 1 by square root x dx, that will be equals to 0 to 1 x raised minus 1 by 2 dx, which will be equals to square root x by 1 by 2, limit from 0 to 1, and it is a finite quantity only, so we'll get 2 1 minus 0, that is 0. So since our integration 0 to 1 gx dx is convergent, so this implies that my integration 0 to 1 minus of fx is also convergent, because fx is convergent, then minus fx is also convergent. So that means that our integration 0 to 1 log x divided by square root of 2 minus x dx is convergent. Now this completes our first part of the question, that is we have checked convergence of I1. Now in order to comment about convergence of I need to check convergence of I2 as well. So let's check convergence of I2. So my I2 is integration from 1 to 2 log x divided by square root of 2 minus x dx. Now in this case also our fx is, let's equate it with 1 to 2 fx dx. Here I am not introducing minus sign because the function fx is positive for all x in between 1 to 2. So our fx is basically equals to log x divided by square root of 2 minus x. Now if I assume any another function, let's say hx as 1 by square root of 2 minus x. Now let's use limit comparison test again. So this time it will be limit x approaches 2, because x equals to 2 is point of infinite discontinuity. log x divided by square root of 2 minus x divided by 1 square root of 2 minus x. This is equals to limit x approaches to log x, which is equals to log of 2. Now this time this limit is not equals to 0 and also it's finite. So we can use limit comparison test that says that if the limit turns out to be non-zero and finite, then both the terms behave alike. So since limit is non-zero and finite, so both terms, both fx and hx behave alike. So now let's check convergence or divergence of hx function. So it is 1 to 2 1 by square root of 2 minus x dx. That will be equals to square root of 2 minus x divided by minus of 1 by 2, and limit varies from 1 to 2. I have added minus because of this minor coefficient of x is minus negative, so that's why we got minus 1 by 2. So it will be equals to minus 2 0 minus 1, that is 2, which is finite. So from here I can say that my hx is convergent. So from here 1 to 2 hx dx is convergent. So that implies that my integration 1 to 2 fx dx is also convergent. Now since my I1 and I2 both are convergent, since I1 and I2 both are convergent, so from here I can say that my I function is also convergent. And we are not supposed to, like in the question, we are not supposed to find the absolute value or exact value of the integration. We are just supposed to check its convergence, and that we have done. We have shown that the function, that the integration that is given to us is convergent. Now let's move on to discuss the next question. So the next question is to check the convergence of the improper integral and hence evaluate it. So in the question they have asked us to evaluate it as well. So now let's see how we can do that. Now the first step here also should be to find the point of infinite discontinuities that are there. So here also first step is to check at endpoints only, then we can move ahead on checking any point that is lying in between those 2 points. So if you observe that at x equals to 0, let's name it as I. It has infinite discontinuity when p minus 1 is less than 0, because when p minus 1 is greater than 0, then integrand is 0 only. Likewise at x equals to x approaching infinity, it has infinite discontinuity when p minus 1 is greater than 0, because when p minus 1 is less than 0, then it will be 1 by infinity, that is 0 only, and it is a finite quantity. So these are the points of infinite discontinuity. Now if you observe that, like we have infinite discontinuity at, if you observe that if I take x equals to minus 1, then also we have infinite discontinuity. At x equals to minus 1 also we have infinite discontinuity, but minus 1 doesn't belong to this integral. Our integration is from 0 to infinity, so we will not count this. So x equals to 0 and x equals to infinity are only points of infinite discontinuity. Now again the another step should be to break the integration in 2 parts. So our I is integration from 0 to infinity x raised p minus 1 1 plus x dx, which is equals to integration from 0 to 1 x raised p minus 1 1 plus x dx plus integration from 1 to infinity x raised p minus 1 divided by 1 plus x dx. Now let's just name them as I1 plus I2 for simplification. So first we'll check convergence of I1 and then we'll move on to check convergence of I2. So our I1 is integration from 0 to 1 x raised p minus 1 1 plus x dx. So if I write it as 0 to 1 fx dx, so here my fx function will become x raised p minus 1 divided by 1 plus x. Now let's choose some appropriate function gx and then we'll move on to apply limit comparison test. Now if I take my gx as x raised p minus 1 only, then what will be my limit? X approaches 0 fx by gx. It will be equals to limit x approaches 0 x raised p minus 1 divided by 1 plus x divided by x raised p minus 1. That is equals to limit x approaches 0 1 divided by 1 plus x, which is equals to 1, and 1 is a non-zero and finite quantity. So from here we can use limit comparison test that says that if the limit turns out to be non-zero and finite, then both fx and gx functions behave alike. Since limit is non-zero and finite, so both fx and gx behaves alike. Now let's check convergence or divergence of gx function. That is basically nature of gx function. So that will be integration from 0 to 1 x raised p minus 1 dx. So if I integrate it, it will be integration from it will be basically equals to x raised p minus 1 plus p, and limit varies from 0 to 1 divided by p minus 1 plus 1, which is x raised p divided by p, and limit from 0 to 1. Now this limit will be equals to, it will be equals to 1 by p when p is greater than 0, but it will be minus of infinity, 1 by p minus infinity when p is less than 0, because when p is less than 0, this will be equals to basically 1 by p x raised p, and if I plug in 0, it will be 1 by 0, that is infinity only. So that's why this is equals to minus infinity only, because 1 by p is a finite quantity. So from here we can say that our function gx is convergent when my p is greater than 0. So this is the condition that I got from convergence of I1. So from here I can say that my I1 is convergent when p is greater than 0. Now I need to find convergence, like I need to check convergence of I2 as well. So my I2 is integration from 1 to infinity x raised p minus 1 divided by 1 plus x dx. Now if I write it as 1 to infinity fx dx, then my fx will be basically x raised p minus 1 by 1 plus x. Now if you observe that 1 plus x is basically less than 1 plus x for all x lying in between 1 to infinity. Now from here what I'll get is 1 by 1 plus x is less than 1 by x, and if I just multiply by x raised p minus 1 on both hand sides, so I'll get x raised p minus 1 divided by 1 plus x less than x raised p minus 1 divided by x, which is equals to x raised p minus 2. Now let's name it as some function hx. So this is basically, I reduce it to a comparison test. Now if my hx is convergent, then I can comment about convergence of I2 as well. So now let's check convergence of hx. That will be equals to integration from 1 to infinity x raised p minus 2 dx, that is x raised p minus 1 divided by p minus 1 integration from 1 to infinity. Now this limit will be equals to, this will be infinity only when p minus 1 is greater than 0, but it will be equals to minus 1 divided by p minus 1 when p minus 1 is less than 0. So hx is convergent when p minus 1 is less than 0, that is when p is less than 1. So from here we got that our I2 function is convergent when p is less than 1, but I1 is convergent when p is greater than 1. So if I just combine the two terms, so if I just combine integration I with I1 and I2, so my I was I1 plus I2. I1 is convergent when p is greater than 0, but I2 is convergent when p is less than 1. So if I combine these two, so my I is convergent when my p lies in between 0 to 1. So this is the interval of convergence. Now let's move on to discuss the other part. It has also asked us to evaluate the integration. Now let's do that. So integration is, I is integration from 0 to infinity x raised p minus 1 divided by 1 plus x dx. Now this integration can be solved in multiple ways. One way is to convert this integration into a beta function. So the original beta function is beta x comma y integration from 0 to 1 t raised x minus 1 1 minus t raised y minus 1 dt. Now if I choose my t as u divided by 1 plus u, so from here I get my dt as 1 plus u du minus u du divided by 1 plus u square, which is equals to, which basically gives me dt as du divided by 1 plus u square. So the above integration, that is beta x comma y, changes to, we'll check the limits later. First let's just see what will be the integrand. It will be u divided by 1 plus u raised x minus 1 1 minus u by 1 plus u raised y minus 1 dt is du divided by 1 plus u square, which is equals to integration u raised x minus 1, this will be 1 plus u minus u, that is 1 in numerator, and in denominator will be left with 1 plus u raised x minus 1 plus y minus 1 plus 2, that is x plus y du. Now let's check the limit. So when t is 0, my u will also 0, but when t is 1, it will be basically, let's just see what will be our u from here. So it will be t times 1 plus u equals to u. So it will be t equals to u times 1 minus t. So from here our u will be t divided by 1 minus t. So when our t is 1, our u will basically approach infinity. So this is integration from 0 to infinity. Now if you observe that this form is basically similar to what we got in our, like what is given to us in the question. So if we just compare, this term is basically equals to beta x comma y, right? Now if we just compare our equations, so from there we have x equals to p by comparing the numerator parts, and x plus y is equals to 1, that is basically p plus y is equals to 1. So from here we got our y as 1 minus p. So our integration I is equals to basically beta p comma y is 1 minus p, and we know what is beta function. So beta function is beta x comma y is gamma x gamma y divided by gamma x plus y. So if we use that relation here, so it will be gamma p times gamma 1 minus p divided by gamma p plus 1 minus p. which is equals to gamma p gamma 1 minus p divided by gamma 1, and gamma 1 is 1 only. Gamma 1, which is gamma p times gamma 1 minus p. Now you can leave it here as well, or you can just use gamma function to evaluate it, or till here is also fine because it's a 15 marker and that's too much of calculation for a 15 marker. So let's move on to discuss the next question. So the next question is examine the convergence of the given integration. So they have given us an integration and we're supposed to check whether this one is a convergent or not. So let's move on to see whether it is convergent or not. So first point should be to check the point of infinite discontinuities. So if I check at x equals to 0, my integrand is basically, that is the log x term basically approaches infinity. So log x by 1 plus x approaches infinity as x is approaching 0. So it will approach basically minus infinity. So from here I can say that x equals to 0 is point of infinite discontinuity. Now if I check at x equals to 1, then it is a finite term only because log 1 is 0 and in denominator we have 1 plus 1, that is 2. And in between 0 and 1 there is, I cannot see any other point of infinite discontinuity. There is x equals to minus 1, but that doesn't belong to 0 to 1. So we can easily avoid that. So x equals to 0 is only point of infinite discontinuity. Now we need to check its convergence at this point. Now let's use some test to see. So if I name my integration as integration from 0 to 1 log x by 1 plus x dx, so it will be equals to 0 to 1 fx dx, where my fx function is basically equals to log x divided by 1 plus x, or let's take it as minus of fx, where fx is minus of log x. I'm introducing this minus sign in order to make the integrand positive because log 0 is a negative infinity. Now let's assume some other function. Let us take some function gx as square root of 1 by x. Now if I check its limit at x equals to 0, that is limit x approaches 0, fx by gx, so it will be equals to limit x approaches 0 minus log x divided by 1 plus x divided by 1 by square root of x, which will be equals to limit x approaches 0 minus square root of x divided by 1 plus x times log x. Now if I plug in the limit, it will be 0 times infinity form. Or let me just write it in a more simplified version. So it will be equals to 1 by square root plus 1 by square root x times minus log x. Now if I just plug in the limits, it will be infinity by infinity form. That's better. Now let's use L'Hopital rule to evaluate this limit. So it will be limit x approaches 0 minus of 1 by x divided by, it will be 1 by 2 square root x, and here we will have minus 1 by 2 x raised 3 by 2. Now this simplifies to limit x approaches 0 minus 1 by x, and in denominator we have, I can pull out 1 by 2 square root x, so it will be 1 minus 1 by x, which is equals to limit x approaches 0 minus 1 by x divided by 1 by 2 square root x, x minus 1 by x. Now if I simplify it, it will be equals to limit x approaches 0. This x balances this one. So we have 2 square root x divided by x minus 1. And there is a minus sign as well. Now if I evaluate this limit, it will be basically 0. So my limit x approaches 0, fx by gx is equals to 0. And in the first question we have seen that whenever this limit is 0, then convergence of g implies convergence of f. Now let's see whether my g is convergent or not. So 0 to 1 gx dx will be equals to integration from 0 to 1 by square root of x dx, which is equals to integration from 0 to 1 x raised minus 1 by 2 dx. That is equals to x raised minus 1 by 2 plus 1 divided by minus 1 by 2 plus 1. Our limit varies from 0 to 1, which is equals to square root of x divided by 1 minus 1 by 2 is basically 1 by 2, and limit from 0 to 1, that is 2. And this limit is finite limit, so from here we can say that my integration 0 to 1 gx dx is convergent. And from here, by limit comparison test, I can conclude that my integration from 0 to 1 log x by 1 plus x dx is convergent. So this completes my question. Now let's move on to see the next question. So the next question says that test the convergence of improper integral. Now in this question also, first we should find out the point of infinite discontinuity. Now if you observe that x equals to a is only point of infinite discontinuity, because that's the only singularity that this integrand have. So now let's see how we can solve it. Like we can solve it directly as well, because it is in 1 by, like it is a p series kind of form, so we'll try to solve it directly as well, directly only. So let's name it as I. So I is equals to integration from a to b dx by x minus a raised n. Now I can write it as limit epsilon approaches a, integration from epsilon to b dx divided by x minus a raised n. Now if I evaluate it, it will be equals to limit epsilon approaches a, integration from epsilon to b x minus a raised minus n dx, which is equals to limit epsilon approaches a, x minus a raised 1 minus n divided by 1 minus n, and limit varies from epsilon to b. Now if we just plug in the limits, it will be equals, plug in the limits, it will be equals to limit epsilon approaches a, b minus a raised 1 minus n divided by 1 minus n, minus epsilon minus a raised 1 minus n divided by 1 minus n. Now let's find out its limit. So the limit will be equals to b minus a divided by 1 minus n when 1 minus n is greater than 0. But when 1 minus n is less than 0, so this limit will basically approaches infinity. So it will be b minus a by 1 minus n raised 1 minus n minus infinity, which is equals to b minus a raised 1 minus n divided by 1 minus n when n is less than 1, and it is minus of infinity when n is greater than 1. So from here we got that our integration is basically convergent. I is convergent when n is less than 1. Also, like, this doesn't comment about when n is equals to 1. So when my n is equals to 1, then also it is minus of infinity, because when n is equals to 1, this will be log of x minus a, and if I plug in the limit, it will be log b minus a minus log 0, which is infinity only. So at n equals to 1 also it diverges. So I is convergent when n is less than 1. Now let's move on to discuss the next question. So the next question says that check the convergence of a given integration. So the integration that is given to us is, let's name it as I. So I is integration from 0 to 2 dx divided by 2x minus x square. Now first let me write it in a simplified form. So it will be equals to integration 0 to 2 dx divided by x times 2 minus x. Now you can easily observe that x equals to 0 and x equals to 2 are point of infinite discontinuities. So x equals to 0 and x equals to 2 are points of infinite discontinuities. Now my next step should be to break down this integration. So my I will be equals to integration from 0 to 1 dx by x times 2 minus x plus integration from 1 to 2 dx by x times 2 minus x. Now this simplifies to, in order to integrate it, what I'll do is I'll just use partial fraction in order to write it. So if in partial fraction form, x comma 2 minus x will be equals to 1 by 2 minus x minus 1 by x times x minus the x plus 2 minus x, and there will be 1 by 2 outside. So this is the partial fraction form of the given integrand. So my I will be equals to integration from 0 to 1 by 2 1 by x plus 1 by 2 minus x dx plus integration from 1 to 2 1 by 2 times 1 by x plus 1 by 2 minus x dx. Now if I simplify it, what I'll do is I'll just directly evaluate. So I1 has, like, this integration has discontinuity at x equals to 1. So what I'll do is I'll just label it as lambda approaches 0, lambda to 1, 1 by 2, 1 by x plus 1 by 2 minus x dx, and here I'll label it as mu. Limit mu approaches 2, 1 to mu 1 by 2 times 1 by x plus 1 by 2 minus x dx. Now I'll just evaluate it normally, and then we'll just calculate the limit by plugging in. So it will be equals to 1 by 2 log x minus log 2 minus x, and limit varies from lambda to 1, plus limit mu approaches 2, 1 by 2 log x minus log 2 minus x, and limit from 1 to mu. So it will be equals to limit lambda approaches 0, 1 by 2. If I plug in the limit, it will be log 1, that is 0, and minus log 1 minus log 2 minus 1, again 0, minus log lambda minus log 2 minus lambda, plus limit mu approaches 0, 1 by 2 log mu minus log 2 minus mu minus log 1 minus log 1. So these two terms again approaches 0, likewise these two terms approaches 0. So we are left with limit lambda approaches 0, log 2 minus lambda minus log lambda plus, here we have 1 by 2 as well, plus limit mu approaches 0, 1 by 2 log mu minus log 2 minus mu, and this simplifies to limit lambda approaches 0, one by 2 log two minus lambda by lambda plus limit mu approaches 0, 1 by 2 log mu divided by 2 minus mu, and that is equals to 1 by 2. If you plug in the limits, this will be like these two terms will diverge, so the integration will be basically equals to minus infinity only. So from here we can say that our I is divergent. You can use comparison test as well in this question, like let me tell that as well. For example, if this is my I1 and this is my I2, so for I1 my fx is basically 1 by x 2 minus x, so here you can choose your gx as 1 by x. Then if you will evaluate limit x approaches 0 fx by gx, that will be equals to 1 by 2, which is non-zero and finite, so both fx and gx will behave alike. Now you can observe that your gx is divergent, so your I will be divergent. Likewise for I2 you can assume hx as 1 by 2 minus x. Now if you will evaluate limit fx by hx as x approaches 2, again the limit will be 1 by 2, which is also non-zero and finite. So you can observe that this is basically 1 by 2 minus x is divergent. So from there we can see that my I2 is also divergent. So you can do by any method, by both the methods result will be same only. So let's see our next question for today. So the next question is to test the convergence of this integration. Now if you observe that, we know that for all x, cos x is less than 1, and for all x belonging to 0 to infinity, one plus x square is greater than 1. So from here what I'll get is 1 by 1 plus x square will be less than, so we are supposed to check its convergence. So what we know that cos x is like absolute value of cos x is less than 1 for all x in between 0 to infinity. So we'll check its absolute convergence, because absolute convergence implies convergence, so we can use that result. So we'll check its absolute convergence, that is integration 0 to infinity cos x by 1 plus x square dx. So it will be less than equals to integration 0 to infinity absolute value of cos x divided by 1 plus x square dx. Since my cos x is less than 1, so modulus of cos x by 1 plus x square will be equals to modulus of cos x divided by 1 plus x square. Since cos x is less than 1, so it is less than or equals to 1 divided by 1 plus x square. Now we can easily use comparison test. So our integration from 0 to infinity cos x divided by 1 plus x square dx will be less than or equals to integration 0 to infinity dx by 1 plus x square. Now we can easily evaluate this integration on right hand side. It is equals to tan inverse x, and limit varies from 0 to infinity. That is tan inverse infinity minus tan inverse 0, and tan inverse infinity is pi by 2, and tan inverse 0 is 0. Now if you observe that we got this integration on left hand side, on right hand side as convergent. Let's name it as integration 0 to infinity gx. Since integration 0 to infinity gx dx is convergent, so from here we can imply that integration 0 to infinity cos x by 1 plus x square dx is also convergent by comparison test. By comparison test we can see that. So this basically completes this question as well, because we are supposed to check the convergence only. Now let's move on to discuss the next question. So the next question says that examine the convergence of this integration, that is 0 to infinity dx by 1 plus x square root of x, and find its value if possible. So this is, let's name it as I. It is 0 to infinity dx by 1 plus x square root of x. Now if you observe that in this question x equals to 0 is only point of infinite discontinuity. I'm writing infinite discontinuity as id. There is x equals to minus 1 as well, but that lies outside the limit of integration, so we'll not consider that. So I can write my I as limit epsilon approaches 0 integration from epsilon to infinity dx by 1 plus x square root of x. Now we can evaluate it directly as well, or based on comparison test as well. So it is easy to evaluate integration, and also we are supposed to find its value. So what we'll do is we'll just directly evaluate it and see if we get a finite value or not. So it will be equals to, if I assume my square root of x as u, so from here I'll get my x as u square. So that basically gives me dx as 2u du. So this will be equals to limit epsilon approaches 0 integration from, when my x is epsilon, my u is square root of epsilon, and when my x is infinity, my u is infinity. So it is 2u du divided by 1 plus u square, and square root of x is u. Now this u balances the 1 in numerator, so it is equals to limit epsilon approaches 0 integration from square root of epsilon to infinity 2 du divided by 1 plus u square. Now it can be easily evaluated. It will be equals to limit epsilon approaches 0 2 times tan inverse u, and limit of u is from square root of epsilon to infinity. Now if I just plug in the limits, it will be limit epsilon approaches 0 2 times tan inverse infinity minus tan inverse square root of epsilon, which is equals to limit epsilon approaches 0 2 times tan inverse infinity is basically pi by 2 minus tan inverse square root of epsilon. If I plug in, if I evaluate this limit, it will be equals to 2 times pi by 2 minus tan inverse 0 is 0 only, so it is 0, and tan is a continuous function, so because of that we are able to do that. So this limit turns out to be pi, and it is a finite quantity, so the given integration is convergent. The given integral is convergent, and its value is I equals to pi. So this completes our question. Let's move on to discuss the next question. In this question also they have asked us to discuss the convergence of given integral. So the given integral, let's name it as I, is from 1 to 2 square root of x divided by ln x dx. Now first point here also should be to check the point of infinite discontinuity. Now if you observe that at x equals to 1, we have an infinite discontinuity, as at x equals to 1, ln x is 0. So this whole thing will approach infinity. Now also that's the only point of infinite discontinuity. So let's see how we can solve this. Now if I can write my given integration as integration from 1 to 2 fx dx, where my fx function is square root of x divided by ln x. Now let's assume another function gx as 1 by x minus 1 in order to use limit comparison test. Now if I evaluate this limit, that is limit x approaches 1, fx by gx, it will be equals to limit x approaches 1. My fx is square root of x divided by ln x and my gx is 1 by x minus 1. This will be equals to limit x approaches 1 square root of x times x minus 1 divided by ln x. Now if you observe that this is basically 0 upon 0 form. So we need to use L'Hopital rule in order to find this limit. So let's do that. It will be limit x approaches 1 x raised 3 by 2 minus x raised 1 by 2 divided by ln x. Now let's apply L'Hopital rule. So limit x approaches 1, 3 by 2 x raised 1 by 2 minus 1 by 2 square root of x divided by 1 by x. Now if I plug in the limit, it will be 3 by 2 minus 1 by 2 divided by 1. That is 1 only, which is a non-zero and a finite quantity. So our limit is basically non-zero and finite. So from here we can say that both integration 1 to 2 fx dx and integration 1 to 2 gx dx will behave alike. Now we need to check what will be the behavior of our integration 1 to 2 gx to comment about the convergence of integration fx. Now integration from 1 to 2 gx dx is basically equals to integration from 1 to 2 dx by x minus 1. That is log of x minus 1 and limit varies from 1 to 2, which is equals to log 2 minus 1 minus log 1 minus 1. That is log 1 minus log 0. Log 1 is 0 but log 0 is minus infinity. So the given integration gx approaches infinity. So from here we can say that integration 1 to 2 gx dx basically diverges, and by limit comparison test integration 1 to 2 fx dx also diverges. So this completes our question. Let's move on to discuss the next question. So the next question is, show that the given integral is convergent and hence evaluate its limit. So first we are supposed to show that it's convergent and then we are supposed to find out the limit to which it converges. So let's see how we can do that. So let's see how we can check the convergence. So I am writing my given integration as I, integration from 0 to pi by 2 log of sin x dx. Now if you observe that this point has infinite discontinuity, where at all those points where sin x is 0. So since sin x in 0 to pi by 2, sin x is 0 at x equals to 0 only. So from here I can say that x equals to 0 is point of infinite discontinuity. Also at x equals to 0, my function fx, if I write it as integration from 0 to pi by 2 fx dx, my integration fx is basically approaches minus infinity. So I'll be using basically minus of fx to apply limit comparison test. So let's assume a gx function as 1 by x raised m, where m I am assuming as less than 1. Now if I evaluate the limit, that is limit x approaches 0, fx by gx, it will be equals to limit x approaches 0 log of sin x divided by 1 by x raised m. Now if I evaluate this limit, if you observe that it is basically infinity upon infinity form. Now if I evaluate this limit, it will be equals to limit x approaches 0, 1 by sin x times cos x divided by minus m x raised minus m minus 1, which will be equals to minus 1 by m limit x approaches 0, x raised m plus 1 divided by tan x. Now again it is a 0 by 0 form. So from here, if I evaluate limit, it will be limit x approaches 0, m plus 1 x raised m divided by sec square x. Now if I plug in the limit now, the limit will turn out to be 0. You can take some specific value of m as well, like m equals to 1 by 2 or 1 by 3 and so on, just for convenience. So from here, since my limit is 0, so if my gx function is convergent, then only I can say that my fx function is convergent. So now let's say what we can say about convergence of gx. So that is equals to integration 0 to pi by 2 x raised minus m dx. That will be equals to x raised 1 minus m divided by 1 minus m. Our limit varies from 0 to pi by 2. So it will be equals to pi by 2 raised 1 minus m divided by 1 minus m, when my 1 minus m is greater than 0. And it will, that's the only case, because I have assumed that my m is less than 1. So that's the only case that we are left with. That is basically m is less than 1. So this limit is finite. So from here we can say that integration from 0 to pi by 2 gx dx converges. And by limit comparison test, we can say that integration from 0 to pi by 2 log of sin x dx also converges. So this basically completes the convergence part. Now we are supposed to evaluate this as well. So we have our integration I as integration from 0 to pi by 2 log sin x dx. Now we also know the result that sine of 2x is equals to 2 sin x cos x. Now if we evaluate integration from 0 to pi by 2 log of sine 2x, so that will basically give me integration from 0 to pi by 2 log 2 plus log sin x plus log cos x dx. Because log of ab is, we have used the result that log of ab is equals to log a plus log b. Now this thing will be equals to, now if I assume, let's assume that 2x is equals to some t, and this I am assuming for the term on left hand side. So from here 2 of dx will be equals to dt. So the limit changes to 0 to pi log sin t dt by 2. And on right hand side we have pi by 2 times log 2 plus 0 to pi by 2 log sin x dx plus 0 to pi by 2 log cos x dx. Now the term on left hand side is 1 by 2 times 2 integration 0 to pi by 2 log of sine x dx. I'm able to write it because the sign, like we have a property of definite integral that says that integration of 0 to 2a fx dx is equals to 2 times integration of 0 to a fx dx if f of 2a minus x is equals to f of x, and it is 0 when f of 2a minus x is equals to minus of fx. Now if you observe that log of sine pi minus x is same as log of sine x, because sine pi minus x is sine x only. So because of that we are able to use this property, and we'll get this on left hand side. And on right hand side we have pi by 2 log 2 plus 0 to pi by 2 log sine x dx plus 0 to pi by 2 log cos x dx. Now this will be equals to integration 0 to pi by 2 log sine x dx plus equals to pi by 2 log 2 plus 0 to pi by 2 log sine x dx. Now there is another property of definite integral that says that integration of 0 to a fx dx is same as integration of 0 to a f a minus x dx. Now if I use this property here, so it will be integration of 0 to pi by 2 log cos pi by 2 minus x dx. Now that will be equals to integration 0 to pi by 2 log sin x dx is equals to pi by 2 log 2 plus 0 to pi by 2 log sin x dx plus 0 to pi by 2. Cos of pi by 2 minus x is sin x only, so it will be log sin x dx. Now if you observe that this is our function I, so we are left with pi by 2 I equals to pi by 2 log 2 plus 2 of I, because these two are I, also I. So from here I is basically equals to minus of pi by 2 log 2. So this is the value of integration that we are evaluating. Now let's move on to next question. So the next question is, show that the given improper integral is convergent. So here also our first point should be to find out the point of infinite discontinuity. Now if you observe that sin x is basically a bounded function, and all its values lies in between 0 to 1. So value of sine of 1 by x will also lie in between 0 to 1, no matter what value of x we choose. So the only infinite discontinuity that can occur is basically due to 1 by square root of x. So if you observe that here x equals to 0 is basically point of finite discontinuity. Now we'll basically use comparison test only, because sine of 1 by x divided by square root of x will be less than or equals to 1 by square root of x for all x in between 0 to 1, because sin x is a bounded function, because sine of 1 by x is less than or equals to 1 for all x. So because of that we are able to comment this. Now if this is convergent, then I can comment about convergence of this function. So let's check convergence of 1 by square root of x. So it is integration from 0 to 1 dx by square root of x. Now here if you observe that it is basically a p series with p equals to 1 by 2. So you can also comment directly here, but if you don't remember the result, you can just evaluate it, because it is easy to evaluate. So it will be x raised 1 by 2 divided by 1 by 2, and limit varies from 0 to 1, that is 2 square root of x, limit from 0 to 1, that will be equals to 2, which is a non-zero and finite quantity. Now this integration 0 to 1 dx by square root of x is convergent. So by comparison test, we can say that integration 0 to 1 sine of 1 by x divided by square root of x dx is also convergent. So this completes our question. Also, we'll be stopping this video here, because otherwise it's already a 1 hour video and it will take too long to upload the video. So we'll discuss the remaining questions on improper integral in next class. So thank you for watching, and please do like, share and subscribe the channel.